Hello everyone, and welcome. I'm excited to introduce today's presentation on anaerobic digesters fundamentals, turning waste into energy. We'll explore how innovative biological processes can transform organic waste into valuable renewable energy and nutrients. This offers a sustainable pathway for waste management and climate action. Over the next few slides, we'll cover the basics of anaerobic digestion, its benefits, and how it can make a real difference. Let's get started. So, what exactly is anaerobic digestion? Well, it's a pretty sophisticated natural process where certain specialized microorganisms break down organic material. But here's the key. It's all happening in environments without oxygen. This process is really important because it naturally decomposes waste and produces two valuable products. The first is biogas, which is a renewable energy source mainly made up of methane and carbon dioxide. Think of it as a sustainable alternative to fossil fuels. The second product is digestate, a nutrient-rich material that's excellent for enriching soils. Now, this technology isn't just a science experiment. It has practical, real-world applications across various sectors. You'll find it in municipal wastewater treatment plants, helping manage sewage efficiently. It's also widely used in agriculture, especially where livestock waste needs to be managed sustainably. And industrial food processing plants are turning to anaerobic digestion as a way to handle waste responsibly. All of these applications tie into our overall theme, finding sustainable, innovative solutions for waste management and renewable energy. Anaerobic digestion is a key piece of that puzzle, helping us move toward a greener future. Let's take a closer look at the 4 key microbial stages involved in anaerobic digestion. This process is like a carefully orchestrated biological symphony, where 4 distinct microbial communities work in sequence to transform complex organic materials into clean energy. Each stage has a critical role, and understanding this sequence helps us appreciate how biogas is produced. First, we have hydrolysis. In this stage, enzymes act like tiny molecular scissors, breaking down complex polymers such as proteins, carbohydrates, and lipids into simpler building blocks, amino acids, simple sugars, and fatty acids. This step is essential because it prepares the organic material for the next phase. Next is acidogenesis. Here, acidogenic bacteria rapidly convert those simple compounds into volatile fatty acids, alcohols, hydrogen gas, and carbon dioxide. Think of this as the fermentation phase, where the organic molecules are further broken down into smaller, more reactive compounds. Then comes acetogenesis. In this stage, acetogenic bacteria transform the volatile fatty acids and alcohols into acetic acid, hydrogen, and more carbon dioxide. This step is crucial because it produces the direct precursors needed for methane formation. Finally, we reach methanogenesis. This is carried out by methanogenic archaea, which are actually the slowest growing organisms in the chain. They complete the process by converting acetic acid and hydrogen into methane, which is the biogas we want to harness. This last step is what makes anaerobic digestion so valuable as a renewable energy source. Understanding these stages highlights how each microbial community plays a vital role, working together seamlessly to produce clean, renewable energy from organic waste. This visualization really helps us understand what's happening inside an anaerobic digester. Essentially, it shows the step-by-step transformation process, starting with the complex organic feedstock, things like agricultural waste, food scraps, or manure, entering the system. As these materials break down through microbial activity, they go through a series of stages, gradually converting into simpler compounds. One of the key outputs we're interested in is methane-rich biogas, which rises to collection points where it can be captured and used as a renewable energy source. At the same time, another important outcome is the stabilized digestate. This is the nutrient-rich material left behind, which is safe and beneficial for reuse, like fertilizing fields or improving soil health. Overall, this slide highlights the seamless transformation inside the digester, turning waste into valuable resources, energy and soil amendments, showing how integrated and sustainable this process is within our broader goals of waste management and renewable energy production. Let's take a closer look at a typical anaerobic digester design. First, the reactor vessel itself is usually an airtight tank, often made from reinforced concrete or specialized steel. The key here is ensuring it stays completely oxygen-free, because anaerobic microorganisms, which are essential for breaking down waste, need a completely oxygen-free environment to do their job effectively. Next, we have feedstock management. These digesters can handle a variety of organic materials, from primary and secondary wastewater sludge to fats, oils, and greases from restaurants, pre-consumer food waste, and even agricultural residues. This diversity is part of what makes anaerobic digestion such a versatile waste management solution. Then there's process control. Modern digesters are equipped with sophisticated systems to keep everything running smoothly. This includes mixers to homogenize the feedstock, grit removal to prevent damage to equipment, heating elements to maintain the right temperature, and automated sensors that monitor temperature, pH, and biogas production. Most digesters operate best at what's called mesophilic temperatures, around 95 degrees Fahrenheit or 35 degrees Celsius. Maintaining this stable temperature is crucial because it supports the delicate microbial ecosystems that are responsible for converting waste into biogas and digestate. Overall, these design features work together to ensure efficient, reliable waste conversion, supporting our broader goals of sustainable waste management and renewable energy production. Let's talk about why using anaerobic digesters can be such a game changer. First, volume reduction is a key benefit. By stabilizing organic waste, digesters can cut the solid's volume by about 30%. This means less space needed for disposal and lower transportation costs, which really adds up over time. Next, odor and pathogen control are significant advantages. These systems dramatically reduce unpleasant smells that come from decomposing waste, and they also destroy harmful pathogens, making the process safer and more environmentally friendly. Moving on, anaerobic digesters are excellent for renewable energy generation. They produce biogas, which can be used for combined heat and power, direct thermal applications, or upgraded to pipeline-quality renewable natural gas, a real step towards sustainable energy. Lastly, nutrient recovery is another important benefit. The digestate left behind is rich in nutrients like nitrogen, phosphorus, and potassium, making it a valuable resource for agriculture, helping to fertilize crops and improve soil health. Overall, these systems support environmental sustainability and resource efficiency, fitting perfectly into our broader goal of sustainable waste management and renewable energy. Let's talk about the real-world impact of biogas on energy and the environment. First, the methane content in biogas can range from about 50 to 75%. That's significant because this methane-rich biogas delivers a high energy density, making it very effective for power generation and heating applications. In other words, it's a powerful renewable energy source. And speaking of renewable, biogas is 100% renewable. It comes from organic waste streams that are constantly regenerating, which means we're not depleting resources or relying on finite supplies. Instead, we're turning waste into a valuable resource. Now, a key point is that anaerobic digestion captures methane, a greenhouse gas that's actually 28 times more potent than carbon dioxide when it comes to trapping heat in our atmosphere. By capturing that methane, we prevent it from being released into the air, which is a huge step toward reducing greenhouse gas emissions. This process also supports the circular economy by transforming what was once considered waste into valuable energy and nutrients. It's a win-win for sustainability and resource management. Let me share a success story. Many progressive dairy farms across the country are now using digesters to generate electricity and heat right on site. This not only cuts their energy costs dramatically, but also virtually eliminates odors that used to bother neighboring communities. Some of these farms even sell excess renewable electricity back to the grid, creating new revenue streams, showing how biogas can be both environmentally and economically beneficial. All in all, biogas technology is a powerful tool in our transition to cleaner, sustainable energy systems that benefit both the environment and our communities. Now, let's take a closer look at some of the challenges and considerations we need to keep in mind with anaerobic digestion systems. First, there's the issue of capital investment. These systems require a significant upfront financial commitment, often running into millions of dollars, and they also demand sophisticated operation. That means we need trained personnel who have specialized knowledge to run and maintain these systems effectively. Next, we have the microbial sensitivity aspect. The methanogenic archaea, which are essential for producing methane, grow quite slowly and are very sensitive to environmental fluctuations. For example, their optimal pH range is between 6.8 and 7.2, and even slight changes outside this window, along with temperature shifts or the presence of toxic compounds like heavy metals or antibiotics, can seriously impact their activity. Moving on to feedstock management, this is another critical point. We need to carefully monitor and balance the input materials. If we don't, we risk process upsets such as acidification, foam formation, or the buildup of volatile fatty acids, all of which can inhibit methane production and reduce system efficiency. Finally, there's the quality of the digestate, the residual material after digestion. Its composition can vary widely depending on the feedstock used, and often it requires additional processing, testing, or treatment before it can be safely applied to land or used commercially. These challenges highlight the importance of careful planning and management to ensure successful and sustainable operation of anaerobic digestion systems within the broader renewable energy landscape. Let's take a closer look at some of the latest innovations and trends shaping the biogas industry today. One key strategy gaining momentum is co-digestion. By blending complementary organic waste streams, like food waste with agricultural residues, we can optimize the carbon-to-nitrogen ratio. This optimization significantly boosts biogas yields compared to using single feedstocks alone. It's a smart way to make the most out of available waste materials and increase efficiency. Another exciting development is the use of smart monitoring systems. These involve advanced sensors, real-time data analytics, and automated controls that help us optimize the entire process. They enable early detection of potential issues, ensuring the system runs smoothly and efficiently at all times. This technology not only improves performance, but also reduces downtime and operational costs. Then, there's the trend of grid integration. As infrastructure for upgrading biogas to renewable natural gas, or RNG, continues to expand, it opens up new opportunities. Upgraded biogas can be injected directly into existing natural gas pipelines or used as transportation fuel. This integration makes biogas a more versatile and valuable renewable energy source. Globally, we're seeing adoption accelerate across various sectors: municipal wastewater treatment plants, animal feeding operations, food processing facilities, and dedicated waste processing centers. This rapid adoption is driven both by tightening environmental regulations and increasing incentives for renewable energy. Overall, these trends are helping us move closer to a more sustainable and efficient energy future. So, in conclusion, anaerobic digesters offer a truly sustainable solution for our waste management challenges. They transform waste into valuable resources by converting disposal problems into renewable energy and nutrient-rich soil amendments. This process not only helps manage waste more effectively, but also generates clean energy, making it a win-win. When we look at the triple bottom-line benefits, we see that anaerobic digestion protects the environment by reducing harmful emissions, creates economic value through energy production, and provides social advantages by improving community conditions and local quality of life. It's a comprehensive approach that benefits everyone. This technology is also a proven and scalable climate action tool. It helps us cut greenhouse gas emissions while promoting sustainable resource recovery and supporting the circular economy. It's a strategy that's both reliable and adaptable, capable of addressing current and future environmental challenges. Ultimately, investing in anaerobic digestion infrastructure means investing in a cleaner, greener, and more sustainable future. As the demand for renewable energy grows and waste management issues become more pressing, anaerobic digesters stand ready as mature, dependable solutions. They can effectively tackle these dual needs, reducing emissions and managing waste simultaneously.